I am starting the stream a little bit early because I have an appointment to go to. So I'm going to try to get in this little extra time. I'm going to check the stream, make sure it works. I am starting this. Okay, so the stream is working. We've actually covered everything we need to cover in the course at this point. I'm going to rely on you guys to seem to have lost my pen here. You have to give me a minute to find my pen. Oh, here it is. I'm gonna rely on you guys to ask me questions. So I'm going to send you an email over the weekend asking for specific questions. But what I want to do at this point is go back and make sure I'm covering a couple of things to the extent that you need to know. So, one of the things that you will be dealing with is beams. And you'll be dealing with this in mechanics and materials and probably the rest of your career. So you really need to know kind of what's going on. The biggest thing is internal stresses, okay? Or what they talk about here is loads. Now, before I start this, again, I'm just going back to cover things. What I want you to do is, if you're watching this, I'm looking for now, excuse me, for you to ask me questions related to certain materials if you feel as though that you're having trouble with some of this. But back to the beams. Let's just say we had a load here. Now, what I'm going to do is kind of show you what you need to know, or what you will need to know how to do when it comes to mechanics and materials. And you need to take this into mechanics and materials. Okay, so if you had a beam and you just loaded it like this, 100 pounds, it was 20 long and say maybe around 8 foot. It's 20 foot. Around 8 foot, you put 100 pounds on it. So of course your first thing would be you might want to label the left end and say the right end. And you might want to take away your supports and say RY. And then you might want to say LY. Now technically this was the type of support that gives you an X. You could sum the forces in the X direction and realize this force doesn't exist. And then you might say, I'm going to sum the moments, say about the right end equals 0. And I will go ahead and in my standard, I make this positive. So this will give you 100. That's the 100 right here. And it exists, if this is 8, I think from my limited math skills that 8 and 12 would be 20. So it's 12 foot over to that. And it's going in a positive direction. The LY is not, and it's 20. So LY would just simply be 1200 divided by 20, scratch a 0, drop it down, and you might get 60 there. Well, two ways you can do the next step. Sum of the force in the Y equals 0. If this one's 60 and that's 100, that's got to be 40. So that would tell you, now I'm going to go back and double check that. So you got 60 and you have 40. Now, let me go back and check that. I'm going to now sum the moments at the left end. And I still have that 100 pounds, but I'm on the left end. So that is going this way about the left end. That becomes a minus 100, and it's sitting 8 over there. And this force is going that way. So what you get is, see, I don't know that it's 40 yet. So right in the load in the y direction is 20. So I get, or y is equal to 800 divided by 20. Knock that off. Half of that gives me back 40. So in fact, I got that. Now, what do we do next? Well, I guess what we could do is become a little bit more, there is a ruler somewhere. Let's see, how do I find the ruler? There it is. I'm going to try to do my best in drawing some vertical lines here. And then drawing a vertical line here. And then I'm going to give up on that real quick. What I'm going to do is I'm going to arbitrarily slice this thing at some location x. If I slice it at some location x, where x is going to be between the beginning of the beam and right to the left of that 100 pounds. So the diagram looks like this. You get 60. And now you got to have an offset now. So you're looking at an offset. Now, let's go back and review for a moment. Positive bending will make this occur. Oops. So you got this, and your moment looks like that. So that's positive bending. Looks like to me I have a positive bending over here. Oops. Positive shear on the right end. Now what we have to remember is, and this is the way I remember it. Okay, you got a direction that's positive, and say, okay, let's do it like this. X and Y. So if you think of a positive shear being related to a negative, then this is positive shear. Here's what I mean. This is the positive direction. Think about it like this. You got a surface and you have a positive normal. Here's your normals. So think about this back in Cal whatever. Here's a surface or an object. Here's your normals poking out of it. Think of it as being a porcupine. Here's your porcupine. Here's all your normals. They're all pointing, they're all vectors. They point in a particular direction. Now, if they're normals, they generally have a length of 1. That's not material anything here, but let's look at the right end here. You have a normal poking out. It's the normal is poking in the positive x direction, so it's this. The positive y goes that way. Now this is your x. So it turns out that the shear goes like this. So I'm going to erase all that in a minute. So let's take a look at this. I have some distance x. It's variable now. So I can slice it at any variable location. Maybe I want to slice it here, maybe here, anywhere. So the question is, what would the values of the internal load be as a function of x all the way up to the point where that load sits? So here we'll get rid of those and we'll look at it that way. So you got a shear and you got a moment. Well, if you sum the forces, you find out the shear is just 60. Okay, and it stays that way. So here's what I mean. Let's draw a shear, what they call a shear diagram. I'm going to borrow my ruler again. Here's the 0 value. Here's 0. Turns out it's 60, and it stays 60 up until that point. So if I vary this, actually I think I can slide this off the screen and draw it back. So if I vary X all the way up to 8 feet, the shear does not change. Now let's look at the moment here on this simple case. Well, if I'm moving this far over and I'm 60, then this moment has to offset such that, and you could do it this way, sum of the moments equals 0, and I'll do it about this location, and I'll make this positive, equals to m minus 60 times x. So therefore, where m is the value that sits right there, the 60 is the load here, the x is this, so we're all good here. So your moment here is equal to 60 times x. So if x were equal to 0, or you were slicing the beam right back here at the left, it would not be anything but 0. So here I'm going to draw this and say, how does this vary as we go from the left end to the right end of this? Here's your moment. And it turns out, this 32 degrees is just random. Just that it increases to the point where when x is equal to 8, hang on, when x is equal to 8, this value is 8 times 6. Here, I am going to, I'm sorry, not 8 times 6, 8 times 60. So if you move here to 8, you're at 480. So about 480. Now, here's 8. Now let's look at something just interesting. Before we go on, let's stare at what we have. What might be the slope of this line? Okay, so the slope of a line, of course, is rise over run. I think I'm going to erase part of this. Slope is rise over run. And so it rose 480. It ran down 8. That's 60. Is that a coincidence? That is the same value as there? No, that is not a coincidence. It turns out that depending on the way you look at it, if you take the derivative of this diagram, you get that one. And if you take the integral of this diagram, you get that one. So depending on the way you look at it, you take the integral of one function, you can take the derivative of the same function and get back where you started from. So in fact, there's a relationship. In this particular case, slope, but you could look at it in a differential level, is equal to that. Now, I don't know that we're supposed to know that yet, but we're just building this. And so I'm trying to give some idea of what happens as you build it. Now I'm going to say, let's say for x, we're going to take another case here. So take another case, I'll say the green. So now I'm going to, give me a second. I'm going to say the green now. I'm going to go here where x is going to be between 8 and 20. So for this case, it looks different. Let's do the free body diagram, but in essence, I'm getting a kind of a crowded space here. So let me do this. And we'll move that to the right. We'll now go back in and say, we're looking at a completely different free body diagram. Here's what we're looking at. Now, if I'm to the right of this 100 pounds, it always sits there. 60, and this is our x. Well, what's the distance from here to here? Well, that distance is 8 minus x. So if x were 10, I'm sorry. Did I say it that way? Anyway, I don't remember what I said. You can rewind it. But anyway, it's supposed to say, if I'm at 10, say, then 10 minus 8 tells me that's 2. So if this were a value of 10, this would be a value 2. If this were a value 11, this would be a value 3. So now, here's my moments. Here's my shear. Wow, interesting. Let's look at the shear diagram. Shear, okay, so let's do it this way. Sum of the forces in the y equals 0 on this object. I get a 60. Okay, I'm making that positive. 60 minus 100 minus v. Move the v over. V is going to be a minus 40. Now here's what happens. The sign convention is important here. So we maintain that this is the direction we point it to. In other words, it remains pointing south here. And it becomes a minus. Well, yes, I know that that means that this vector flips over. But for the sake of this plot, that is not kosher. What we need to do is we need to come in here, and from about here to here, the value is minus 40. Now, if you want to, and you can do this, you can basically draw this line. And guess what this height is? It's 100 from here to here. So let me pause here for a second. I got to send a thing for this meeting. All right, I'm back. Meeting got delayed for a minute, but that's okay. That gives me a little bit more time here. Okay, so here we're sitting. Moves down 100. Why? Well, because somebody put 100 pounds on it. So the shear diagram looks like that. Well, guess what? Let's just make this assertion. Let's prove it. Should it go back to that? Okay. Let's prove that. Well, first of all, let me jump ahead and say, if this truly is the relationship, that this is the case, wouldn't the slope of that line have to be 40? So if you took minus 40. So if you took that and took the derivative of it, it should take you back to 0. Now I'm saying this, but let's go in and make sure we can prove this. I should have done it and then looked back at this, but let's go ahead and do this. Okay, now I'm going to sum the moments where about the end that you have the internal load at. Now, here. I'm going to make it go like that, and then I'm going to point to right here, equals 0. Now, of course, I have to include this moment because that's the end moment. M minus, oh, well, I should do a plus because this one is going that way. So that's 100 pounds times, what is the distance between here and here? Oh, well, it happens to be that. X minus 8. And then you got this load all the way over here, the 60 pounds going the other way. So that makes it minus, didn't move this over. Okay, so what I'm going to do, here's what I'm going to do. Minus 60 times x. Why? Because the distance from this place to the end of the beam that you're looking for the internal loads, and this 60 pounds is x. Now what I'm going to do, give me a second here. Cramping the diagram again. Writing small, then big, then... Okay. Move it over. Okay. Then what I'm going to do, here's what I'm going to do. Go ahead and take this. Move it right there. Okay, so now I can take this junk, move to the other side, and again, my goal is to find that m is equal to 60x minus 100 times x minus 8. Okay, now I got 100x right here, and I got 60x right here. So I've got 60x minus 100x. Minus and that minus gives me 800. And then I got this, which gives me minus 40x plus 800. And I got an m. Okay. Now let's play around here. What happens if x is equal to 8? Now, x was equal to 8 where that load was applied right here. So if x were equal to 8, what would that be? That'd be 800 minus 40 times 8. Okay, and what would that moment be at x equal 8? Okay, give me a minute. I got my calculator over here. Oh, come on, phone. Okay, calculator. Okay, 800. Well, first, 40 times 8 gives me 320. Take away that 800 gives me, wow, 480. Okay, so let's stare at that, and let's look at what we found out from the last point. From the last point, it turns out that just to the left of that load is 480. Now, just to the right of that load is 480. But what we have here at this particular point, what's the slope? Well, geez, that's a tough question there. Slope could be, oh no, has it got this problem again? I have this problem occasionally. Did I lose the ability to select a pen? Okay. Okay, guess what I'm going to do? Don't know why. There we go. So now, go back to draw. Now I can select pens. Don't know why. Okay, so guess what? What is the slope here? Is the slope this? Is the slope this? Is the slope this? Is the slope this? At this particular point, I don't know. So it's that undefined thing. Right here is like the slope could be anywhere from this value, which would be this, to this value, which guess what? Would be that. But the slope could be here. Well, that might be somewhere right around here. And here, maybe that's somewhere around here. So this is a very strange point in that it's singularity, so to speak. the slope is actually undefined, but bounded. It's bounded by the minus 40 and the 60. But guess what happens then? Okay, so here's my equation. I'm going to copy this up here so I can monkey around with it. That's too many of those things. M is equal to 800 minus 40x. Was that right? Yeah. So first thing I see, what's the slope? Okay, I don't know. But let's see. If I'm to the right of this, dm dx, taking the derivative, that 800 goes away. I get minus 40. Oh, crap. Look at this. That's what sits right there. So suddenly you start seeing that maybe there's a relationship between the moment and the shear. And there is. And in fact, it's the derivative. One's the derivative of the other. And obviously you can see it's pretty spot on, because when you have a weirdly defined point, the slope is bounded. And so now you can just go out here and say, well, what happens if what is the moment at 20? Well, let's see, 800 minus 40 times 20. That's 2 times 4 is 8, 2 zeros, and you get a 0. Interesting. So it's a straight line from 480 to 0 with a slope of minus 40. Now, this kind of makes sense. Let's look at the beam and the drawing. Here's your beam as it sat alongside the road or wherever it was. Nobody is torquing the beam up. Nobody is putting a moment on the end. These are what are called boundary conditions. There's a boundary. There's the left boundary. Here's the left boundary. Here's the right boundary. Did somebody put an axial load here? Or an axial load here? That's a boundary condition. Did they put okay, go away. It's not going away. Okay. Did they put a moment on the end? Was there somebody out here attaching a wrench and twisting it? Yeah, I didn't see anybody doing that. That wasn't a prescribed load. So in fact, there's no moment on the left, and there's no moment on the right, and no moment on the left. And in fact, if you look at this, the boundaries indicate that being the case. Now somebody's saying there's a boundary load of 60 on the left and minus 40 on the right. Well, somebody had to hold the beam up in the air, so there's that. So in fact, these are what are called shear and moment diagrams. And without getting through too much detail, I'll kind of display it like this. Okay, so, and I don't want to, I kind of hesitant to do this, but I'm going to do it anyway. There is an equation that looks like this. This is actually the beam equation, in which W is the deflection. And guess what I is? Most of the time they list them as I, but if you had a beam that's frontal area looks like this, and you find that X and you find that Y, guess what it is? 1/12 base times height to the third, where that's the base and that's the height. And what is E? That's the stiffness. For example, I think that was introduced in materials. I don't know. For steel, it's pretty stiff, meaning that it's a spring constant. If you have a stiff material, let's say, for example, you had a column that was 1 foot of steel and you pushed it with 100 pounds, it might deflect a little bit. Now you take a rubber column, you push it down with 100 pounds and it squishes quite a bit. So, here, 30, okay, well, E to the 6 PSI, or pounds per square inch. That's generally the modulus of steel. For aluminum, it's this. It can go down a little bit from that. So aluminum is a more flexible material. It will flex more under the same exact load that steel will, by a factor of 3, or roughly 3. So in fact, this is where you think of the E as being the equivalent of defining a spring constant for a spring. Beams are springs anyway. So what happens here? Well, sometimes you'll see in some materials, anyway, I'm not sure I want to go any further, but buried in this, you will find the fact that, here, I should put that as a square. This is not, this might be equal to a load, some sort of distributed load. So I'll say f of x, and then I'll say this might be the beam equation. The f of x could have point loads in it, but in some books will list this, and this is actually the shear. Guess what happens when you take that extra derivative or take away the derivative? You're going to get the moment out of this. And so I guess I could do like that. I shouldn't have done it that way. But anyway, you can do that being the moment, and then you can take the derivative of the moment with respect to x. Well, that's the derivative of dx of ei d second d. And you can go on from there. Did I say that? Oh, yeah, I did. And that's the shear. So there is a reason that you did this. You were not introduced to this in this course, but you probably were introduced to this in, I guess that's called materials, the materials course. These two together, and the application of this equation can give you the deflection of a beam. So, for example, you can have a very, very long beam that's very thin and it's pushed down. Thin meaning that this value, I, might be too small for what you want. So it deflects down maybe too much. Maybe this is a beam or rafter on a roof, and you put all this weight on top of it, and it starts deflecting down. Well, you might get cracks in the wood on the shingles up there, and it might leak. So you might not want it to deflect too much, deflection being W. This is all introduced to you, not in this course, but in mechanics and materials. So let me get all this junk off here. But I wanted to give you perspective because you will have to, hang on. Oh, that was not me writing on the screen. That was a piece of dust on there. You will have to understand this and solve these equations in mechanics and materials. These are fourth order differential equations. That might not be how you approach them, but I can guarantee you, you will have to know how to do a shear and moment diagram. Whoops, hang on. So here is, in fact, what's often called a shear and moment diagram. I'm sort of avoiding that, so I can get rid of this and get rid of this. So this you will have to know. If I don't receive questions about some of the material, I'll probably do some more of this on Monday. But if you have questions, come in on Monday and ask them, or ask them and send them over the weekend, and I'll address them in the live stream. You don't have to come, but to have your questions answered, you do not have to be there, but you have to ask them. And so with that, we have been running for 35 minutes now. So we have not officially made the 45 minutes to 50 minutes, but this is 35 minutes of intense time, whereas most classes you'll waste 5 or 6 minutes talking and going on from there. So currently the time is 10:58. I did start this a little bit early because I have to go to a meeting and take some material to the meeting. I will try to introduce you to this concept, and that is what happens. Now there's another relationship here. Okay, so if you think about it, let's look at what we had. We had a point load, call it P. Our diagram went like this, bing, and like that. And we had a moment diagram, went like this. It turns out the load, okay, so here I'll say load, I'll say shear, I'll say moment. Believe it or not, this diagram is related very distinctly through a derivative, integral, to this. So in essence, you could take the beam away and you could say, what is this? There's a thing called a delta function. And a delta function is, let me kind of give you an idea. It's a point load, it's a point, oops. So here's a f, okay, so let me give you an idea. X, here's y, for example. Here's a delta function, okay. It looks pretty ugly. Dx. And this is a certain height, which I'll just call HE, for example. Turns out a delta function has a pretty interesting behavior in that the area here has to equal 1. So that means HE dx equals to 1. Now, this is a delta function. This actually is infinitely small, but this would be infinitely big in order to get that area. Why do you want that? Because essentially that's what this load is. It is a delta function. There is no real such thing as a point load. A point load would be smaller than an atom. It doesn't really work. There is some sort of distribution here that is ever so small that is being pushed down here such that the total area, okay, think about it like this. Remember we had the distributed loads where we stacked all these bricks, right? Now we stack a lot of bricks really high, and to the point where I have all these bricks stacked, and the total weight of all the bricks in our case was 100 pounds. It was applied over a very, very small area, but not 0. So in fact, mathematically, this is written as that P was 100 pounds times the delta at X was at, did I say it was at 8? I think I was at 8. Yeah, it was at 8. Now when I reach class next time, we'll monkey with this one a little bit to give you an idea of what this is. But my point is, what I might go to instead is this. What happens if I have a triangular load? Or what happens if I have just a simply distributed load on a beam? What does the shear diagram look like? What does the moment diagram look like? So I think this is where we'll go next. I think we'll start here. We'll work through the shear and moment diagram. Then we'll, if we can do this on Monday, and maybe we can do this one on Monday as well, but if not, we'll do it on Wednesday. What does the shear diagram and what does the moment diagram look like here? What's the relationship between this function and this one and this one? And we'll see that there is a relationship between those. So we'll do that on Monday. And for right now, I have already spent 40 minutes, and we'll go from here.